All right, the unit circle, this one always strikes fear in a lot of people, and it really doesn't need to be that bad. Just work with it until you are comfortable with these these angles, the coordinates that go with them, and you just want to be efficient. Here's the bottom line, you don't want to spend time trying to count and figure out where something is on a unit circle during a test or a quiz. You're losing precious time doing that. So you really want to kind of have this memorized probably by the end of this section, really. In calculus, you're really going to be expected to have this memorized. So be working toward that. Work with it till you're familiar. That's what I'm going to leave it as. So to understand the unit circle, we really need to start with our special right triangles. And there was two of those. You had a 45, 45, 90, 30, 60, 90. 45, 45, 90 triangle. So if one side was, say, 1, all right, well, there was a rule from geometry that if the angles are the same, it's isosceles, so the sides have to be the same. So if that's 1, then this also has to be 1. And we could just do Pythagorean theorem to do the rest. One leg plus the other one squared would equal the hypotenuse squared. So that would be 2 in this case. So square root of 2 would be the length of the hypotenuse. When we do 30, 60, 90, I always like to kind of start with this little bit of background. So let's say we start with an equilateral triangle where each angle is 60 degrees. To make it easy, let's just make each side be 2. And the reason I'm going to go with 2 is because this is really just a 36 or a equilateral triangle split in half. If we split that exactly down the middle, then we now have two 30-degree angles here and here. So I'm just kind of turning this on its side. That's the way to think about it. I think it's the best way to look at it. So that would mean the hypotenuse is still 2. And the short side is exactly half what it was, so it's now 1. So the shorter side's 1. And we can just do Pythagorean theorem to figure out the other side. So 2 squared would have to equal the piece I don't know squared plus this side 1 squared. So 4 would equal x squared plus 1, which means x squared would equal 3. So that piece will be square root of 3. So those are your side lengths. Whatever this side is, take half of it for the short one. Take the short one, multiply by square root of 3, and that's your middle leg. And again, on the 45, 45, 90, these two sides are the same. Multiply this side by square root of 2 to get that one. The reason it's called unit circle is because the radius of this circle is 1 unit. So when you start trying to put triangles on the circle, then their hypotenuse is also the radius. So we want to take our special right triangles and make sure the hypotenuse is always 1. So think about what would we have to do here to make this side be 1? Well, let's try dividing by square root of 2. All right, so let's just do that to all sides. Basically, I'm just scaling it down. Now, if I do that, this is now 1. We want to rationalize these. So multiply by square root of 2 over 2. And if you rationalize, multiply that, you get square root of 2 over 2. And that's the way we want to go. So for the unit circle, if this side's 1, this side is square root of 2 over 2, and so is this side. For your 30, 60, 90 triangle, if you want the hypotenuse to be 1, you'll need to divide everything by 2. That one's a lot less work to do because that comes out to be a half, that comes out to be square root of 3 over 2. So let's put that in here. This is now 1, so this short side's a half. The middle leg is square root of 3 over 2. So those are the side lengths that we're going to want to go with on the unit circle. So now let's think about what happens when we put these things on the unit circle. And I'll start off in degrees, and then next I'll go to radians. Degrees usually, again, is what most people are more familiar with. Seems to be a little bit easier in the beginning. So 30-degree angle. If I put that triangle on there where the 30-degree angle is right here, that looks just like the triangle I have over there. So I'm going to go up a half over square root of 3 over 2. And what you do need to realize is that the point on the circle that goes with that 30-degree angle is the square root of 3 over 2 for the x-coordinate this way, and y-coordinate you went up a half, so that's the coordinate that goes with it. And just kind of while we're looking at this, you probably remember, and we'll go over this more in detail later in the year, you probably remember in geometry the equation of a circle is x squared plus y squared equals r squared. If you think about that, that's just Pythagorean theorem. One side squared plus another side squared equals the longest side squared, which is the radius or hypotenuse. So really all we're doing is, a circle is defined as an infinite number of triangles. It's defined by the Pythagorean theorem. So really we're just sticking these triangles on the circle in different specific places to kind of see what points go along with them. Now if you go with the 45-degree triangle, so that one again looks like this. You're going to go over square root of 2 over 2, up square root of 2 over 2. So that coordinate would be square root of 2 over 2, square root of 2 over 2. Now, right now it seems kind of arbitrary why I'm doing all these coordinates. Later when we get into sine, cosine, tangent, all those good old ratios, that's where these coordinates become super important. If I do a 60-degree triangle, so really that's just this triangle kind of flipped around. So now the short side, the x direction is a half, and the longer side, the longer leg is square root of 3 over 2. So the same thing as the 30-degree angle, just kind of switched around a little bit. Now we get to here, but don't think too much into a 90-degree angle. You get to a 90-degree angle, you're just going up 1, and you're not going over anywhere. So 0, 1 would be the coordinate that goes with that. And you can continue this process. The first quadrant is really all you need to know. If you can remember the first quadrant and what the coordinates look like, you can get the rest pretty quick. Over here, this would be a 120-degree angle. It would be negative a half and positive square root of 3 over 2. And everything over here just mirrors what you've already got. You're just going to have negative values for your x values, and the y's are going to be positive. You can see that just looking at the coordinate plane. So rather than spend time filling all of these in, if you look on page 266, the book actually does this on 2 different circles, but it gives you all of these coordinates. It does them on 2 circles, so they're not quite as cramped as they are on mine. So check that out and make sure you're good with all of these coordinates. You do need to have them all. You need to be able to generate them very quickly. But again, just know the first quadrant, and then you can think about your signs, where they're positive and negative, and get the rest pretty quick. For radians, I really just want to focus on the angles. The coordinates are going to be exactly the same. And you can go through and convert each. You can convert a 30-degree angle to pi over 6 radians. You can convert a 45-degree angle to pi over 4 radians. You can certainly do that. It's kind of cumbersome. I wouldn't recommend it. This is the easiest way I know to explain where the angles are in radians. And I think it's pretty efficient. So let's start with, of course, 0 degrees if we're going on the positive x-axis. Now we talked about what a radian is. A radian is the radius stretched across the circumference of the circle. And if I go a half a circle, actually let's go full circle. If I go a full circle, it takes 2 pi radians to go all the way around. So that could be 0 or 2 pi if you've gone all the way around the circle. Well, this is half a circle over here, so this is pi radians. This is a quarter circle, so it's half of a half, so pi over 2. If that's pi, it's half of that, so pi over 2. 45 degrees is it's half of a quarter of a circle, so if this is pi over 2, it's half that, it's pi over 4. So I'm going to continue on those and fill, let's do the quarter circles first. So pi over 2, pi, this would be 3/4 of a circle, so 3 pi over 2. All right, let's fill in these 45-degree angles next. So 45 degrees, we said, is pi over 4. If you think about it, that's really 2 pi over 4. 2 pi over 4 reduces down to that. So the next one's going to be 3 pi over 4. 4 pi over 4 will be just pi. The next one's going to be 5 pi over 4. This is 6 pi over 4 and 7 pi over 4. So there's all of your pi over 4 angles, all your 45-degree angles. Okay, we talked about I think 60 is probably the next easiest thing to go. So think about this. If you did 60-degree angles, you would have 3 of those in your half circle. So divide your half circle of pi into 3 parts. And that's going to be pi over 3. This one would be 2 pi over 3, which means that would be 3 pi over 3, and that checks out. So this is going to be 4 pi over 3, 5 pi over 3, and ultimately 6 pi over 3 is the same thing as 2 pi, so that seems to be pretty good. All right, lastly, a 30-degree angle. Well, if you had a half a circle, you could have 6 30-degree angles throughout it. Now the good thing is most of these you've already done at this point. So if you can have 6 of these, and a half a circle is pi radians, pi over 6 is 30 degrees. Of course you can convert that if you want to. And just kind of keep that same method. Well, 2 of these would be 60 degrees. 2 pi over 6 is pi over 3. 3 of them, 3 over 6 is a half. 4 of them, 2/3. 5 pi over 6, we don't have that one yet. Okay. 6 pi over 6, 7 pi over 6. And if you count all the way around, 11 pi over 6 is this last one we don't have yet. I'm going to include this slide on here, just run through it briefly with you, but again, this is on page 266. I just want to point out that really there's a lot of repetition. If you know the first quadrant, you should be able to get everything else very quickly. Just keep in mind, x values are negative in the second quadrant, y is positive. When you get to the third quadrant, both x and y are negative. When you get to the fourth quadrant, your x is positive, your y is negative. And I'll post this on the notes if you need to take a look online. So now we're up to our trig functions, and this makes a lot of people cringe, but they really don't be too bad. And after I kind of run through the lingo with you, I'm going to try to give you a way that's going to make a whole lot of sense and show you that this stuff isn't made up. It's got some pretty concrete ideas to it. So for all the stuff I'm going to do, I'm going to use O for opposite, A for adjacent, H for hypotenuse. Quick run through, hypotenuse is the longest side. Wherever your angle is, the side that touches that's not the hypotenuse, is the adjacent. And the side that does not touch your angle, that's across from it, that's your opposite side. So that's how we use the terminology. Now sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. And tangent is opposite over adjacent. And when you're in class, I'll show you a fun little rhyme that you can use and you'll never forget those. Cosecant is going to be the opposite of cosecant is the opposite of sine. Secant is the opposite of cosine. Kind of weird how that works. The naming, it goes back to Greek from what I understand, but anyway, just remember cosecant is the opposite of sine, secant is the opposite of cosine. So you just flip those over. And cotangent is the opposite of tangent, so we can just flip those over. Let me try to give you some insight now that we talked about what they are. So let's consider side, opposite over hypotenuse. And let's look at that special case of a 30, 60, 90 triangle. So we know that the short side would be 1, long side would be 2. So think about this. Sine is opposite over hypotenuse. So what it says is that for any 30-degree angle, the opposite side to the hypotenuse is always this certain ratio or percent. Think of it that way. Percent's a good way to look at it. So go ahead and punch out the calculator. Take a second. Punch in sine of 30 in the calculator if you don't know what it is right off. So for sine of 30, you should have got a half, or in the calculator you get 0.5, so about 50%. But it should be kind of consistent with what we're seeing, that you get 1 divided by 2 when you do opposite over hypotenuse. So for any 30-degree angle, this side is exactly half the hypotenuse, and that's for 50%. Now do this one for me. Sine of 60 degrees. All right, you should have got about 0.87 for that. So think of it in percentage. That's about 87%. So if you have a 30-degree angle, this adjacent side is about 87% of the hypotenuse in length. So that's a good way to think about it. Just think about how these ratios go. They're almost like percentages. This is the percent of the hypotenuse that the opposite gives you. And then if you did it for 60, it's the percent this opposite side occupies of the hypotenuse. All right, let's put it all together now. We're going to find the 6 trig functions for a particular angle. Put 2 up here because, in all honesty, if you can remember sine and cosine, you can do all of the rest. If you just get those 2, sine and cosine, they're 2 most important. I promise everything else falls into place from those. We'll work on some identities throughout the year, but everything else will come into place. All right, so you got to go back to the unit circle a little bit. This is where I want to hopefully see that you're getting comfortable with this. So on a unit circle, 5 pi over 6 is this angle over here. And I don't want you having to think about degrees to get it. I want you going straight to that coordinate that's on the unit circle that goes with that. All right, well, you can use what we call a reference angle if you'd like. And if you want to think in degrees, that's okay, but it'd be good to be thinking in radians here. So it's the same thing as if we drew a triangle right here that was pi over 6 radians. So that long side, that's going to be negative square root of 3 over 2. And you're going to go up positive a half. So those are the coordinates that would go with that point. All right, well, when I go to do sine of 5 pi, I'll tell you what, for simplicity, I'm just going to say sine of the angle so we don't have to keep writing all that over and over. So sine of that angle. Okay, so again, it's the same thing, a 5 pi over 6 angle, it's the same thing as what we call this reference angle. If we drew a little acute angle in here, it would use the same coordinates, so that's a smarter way to do it, I think. So the sine of that angle would be 1/2 over 1, so a half. Cosine of that angle would be the adjacent over that hypotenuse, so negative square root of 3 over 1, or negative square root of 3 over 2 divided by 1. And that's the good thing about the unit circle part. Hypotenuse is 1, so divided by 1 doesn't change anything. Now I told you, all you really need to know is those two things. Once you've got those, everything else is pretty easy. You just divide these two things by each other, and that's your tangent. Or you can do opposite over adjacent, that's fine too. So 1/2 divided by negative square root of 3 over 2. Now play that out. You'd have to multiply a half by 2 over square root of 3. Answer is going to be negative. The 2's would divide out, but you have 1 over square root of 3. You want to rationalize that. And this is why you want to memorize it. You don't want to have to do this every single time. This is pretty tedious. So tangent would be square root of 3 over 3. In this case, negative because of where it falls. So negative square root of 3 over 3. All right, so I think it's probably worth your time to go ahead and memorize the ones for tangent as well. Now, cosecant is going to be the opposite of sine, so 2 over 1. Secant, now it will involve a little bit of rationalization. So negative 2 over square root of 3, we want to rationalize. So negative 2 square root of 3 over 3. And then for cotangent, same deal is going to happen. We're going to have to flip that. So that's going to be negative 3 over square root of 3, rationalize. We're going to get negative 3 square root of 3 over 3. We can reduce that a little bit. So we're going to end up with negative square root of 3.